Let me put it down in coordinate notation. Okay, in coordinate notation it is rho partial of Vi with respect to time, where we remember that any point xk equals phi k. Okay, and here we have minus the divergence, so we have sigma ij comma j minus body force index I equals 0 for all x, well, it doesn't matter, for all x belonging to omega sub t. Okay? All right, so that is our balance of linear momentum, right? Both in direct notation and in coordinate notation. What I want to do next is look at our balance of angular momentum and reduce it also to pointwise form. Okay, so for balance of angular momentum, so the form that we had was the following: integral over omega t x cross rho material time derivative of the velocity, right, dv. Let me now take the early step of moving everything to the left hand side, okay, over the form in which we had it previously. Okay, so this is the moment coming in from the body force minus the moment that arises from the surface tractions. Right? This is what we have. Now, again, we observe that everything works out just fine except for that surface integral. Okay? And as we did before, in the surface integral, we are going to replace the traction with Cauchy's theorem, which says that the traction is, that T is sigma n. Okay? And then we're going to just work with that term. Okay? So we're going to say consider that term, right? Right? And in particular, what I'm going to do now is to write this term in coordinate notation. All right? So, now in coordinate notation, okay, we have integral over the traction boundary subset. Now, I'm going to construct this coordinate form, okay? So let me first write the sigma n term. Let's suppose we have sigma ij nj. Okay? Now, that's a vector, right? Because the j index gets contracted out, there's a free index only I. That vector with free index I is being crossed by x. Okay? So, let me write an x here, x sub k, all right? And you recall now how things work out with our writing the cross product in coordinate notation. We use our permutation symbol, okay? And in the permutation symbol, we are going to have epsilon k, I, and L, okay? All right? So, if you look at how the indices work out, this integrand has free index L, okay? And because our equation is a vector equation, right? This surface integral also, once the cross product has been taken and you integrate it, still leaves you with a vector. Okay, so we have all this multiplying EL dA. Okay, now the EL can be viewed as just coming along for the ride, and we can choose to just work on the initial part of it, right? That is, we can choose to work on just this part, knowing that whatever we get is going to have free index L, and that's going to be multiplied by the basis vector EL. Okay, so let's look at that, and let me just look at that. Okay, so that's epsilon KIL sigma K. Okay, so we have integral over this epsilon KIL sigma K, sorry, xk sigma ij nj. All right, now the other way to look at this is we can put parentheses here. If you look at what we have within the parentheses, and if I didn't make any mistakes, and yes, I did not make any mistakes, we have free indices Lj, right? So effectively we have a tensor with free index Lj being then, which then acts upon our vector Nj. Okay, so what we can do here is essentially apply divergence theorem to the tensor within those parentheses. Okay, so by the divergence theorem, this is now an integral over omega sub t, right? Epsilon k I L xk sigma I j, and now the divergence involves a we're applying divergence theorem here. So the divergence involves a derivative, right? A gradient term. This is comma j, right? Corresponding to the j index on nj, on n. Okay, but now this is an integral over the volume. Okay, and this is Gauss. Okay. All right, but now we can just compute that gradient, right? In computing the gradient, observe that the permutation symbol is a constant, right? It's just a set of numbers. So nothing happens to the permutation symbol. Okay, so it's epsilon KIL. Okay, let's do it. Okay, so now, and then we just apply the product rule, right? So the derivative of xk with respect to xj gives us the Kronecker delta. So we get delta kj sigma ij. Okay, right, plus epsilon KIL xk sigma ij comma j dV. Okay, now in this expression we are going to leave the second term alone. For the first term, we are going to observe that the combination of delta kj and sigma ij allows us then to essentially rewrite that with different indices on the sigma, because that's what the Kronecker delta does for us, right? So we get from here, we get sigma, sigma ik, but okay. So what's happening here is that the j index on sigma gets converted to a k, so we get sigma ik, okay, plus the next term which just stays the same. All right. Now, here's what happens. If the stress is symmetric, okay, all right, now if sigma ik equals sigma ki, what it implies is epsilon kil sigma ik equals 0. Why might this be? What I'm saying is that if sigma is a symmetric tensor, then its contraction with the permutation symbol is 0. What property would you need on the permutation symbol for that to happen? When you take a contraction of a symmetric tensor with something and it is 0, what does that other something have to be in general? Think about it for a second. It has to be skew symmetric. Okay? And indeed, epsilon I, the permutation symbol is skew symmetric because when we flip the order of the indices of any two indices on the permutation symbol, we change the sign. Okay? Right? So with regard to any two of its indices, the permutation symbol is indeed skew symmetric. However, the stress tensor, if it is symmetric, then it means that that product drops out. Okay? Let's suppose that sigma is symmetric for now. The Cauchy stress is symmetric. Okay? So what that implies is that it tells us then that what we started out with here, this integral, the surface integral, equals just integral over partial omega t, right? Sorry, we've now already gone to an integral over the volume. Right? So we have epsilon k I L xk sigma ij comma j, and just to get things right, I'm going to also include our basis vector here. Right? Sorry, that was an EL. Okay, so all of this EL. Okay? But now if you look at this form, observe that this is a vector, that is a vector, and the effect of this epsilon k of the permutation symbol is essentially to give us a cross product of those two vectors, of the x and sigma ij comma j, and the divergent sigma vectors. So this, if we write it now in direct notation, is just x cross divergence of sigma, where the divergence of sigma is itself a vector, right? So we can take that cross product. Okay? So that's what we have. So that last term is what we are left with when we started out from this equation here, right? Okay? What we've done is work on that last surface term to convert it also into a volume term. Okay? When we put everything together, we have for our balance of angular momentum we have the following, right? We have integral over omega t, x crossed with a bunch of terms. The first is rho multiplied by the material time derivative of the velocity. The next is essentially x crossed with the divergence of sigma, and this is the term that we worked out using the cross product, right? And the Gauss divergence theorem, minus the body force, okay? X cross the body force. And of course, the first term involving the material time derivative of the velocity and the body force did not play any role in our manipulations, but the others did, right? Or the other one did. Now, this is what we have. But what do we have here in the parentheses? In the parentheses there, we have, in fact, our pointwise form of the balance of linear momentum, right? Which we've already established is equal to 0 for all x belonging to omega t. Okay? and this comes about from the balance of linear momentum. What this implies is that our balance of angular momentum is automatically satisfied because the balance of linear momentum has already been proved, right? Has already been proven. But there is a condition. Can you figure out or recall what the condition was? It was essentially what we had before, right? We could not have got here if we had not used this result, right? If we had not supposed that sigma is symmetric, we could not have arrived at our balance of angular momentum. Okay? So what this implies is that balance of angular momentum is assured if sigma equals sigma transpose, right? Or in coordinate notation, we have sigma ij equals sigma ji. Okay? Now, for the type of elasticity that we are considering here, for the type of mechanics we are considering here, it is okay to assume that the stress is symmetric, the Cauchy stress is symmetric. Okay? And given that condition, balance of angular momentum is satisfied. Now, probably in your study of mechanics of materials in your undergraduate days, you were given the same result in the sort of backwards, right? You were told that if angular momentum holds, and you were told that, well, in general, angular momentum holds because little neighborhoods in this body are not spinning around on their own, right? That means at every point in the body, angular momentum is conserved, all right? And that was given to you as an explanation for why sigma is symmetric, right? The stress is symmetric. What we're seeing here is effectively the same condition, except that we're saying that, well, let's assume that the stress is symmetric. What that gives us is that angular momentum is satisfied, right? And by observation, angular momentum has to be satisfied for this condition. Okay? Now, just as an aside, there are other theories of mechanics and elasticity where it is not sufficient to assume that the stress is symmetric, okay? That even the Cauchy stress is symmetric. All that does is that it means that there is an extra term in our balance of angular momentum equation, and that therefore the balance of angular momentum equation also needs to be ensured or needs to be imposed just like the balance of linear momentum. Okay? Otherwise, in our standard study of mechanics, which is what we will pursue in this series of lectures, we do not explicitly solve for the angular momentum condition, right? Assuming that the stress is symmetric, right? That's essentially the sort of mechanics we're going to pursue in this series of lectures. And here is also a good place to stop this segment.